Section 8.2 is transformations of log functions. So it's exactly what we've done in chapter 1, 2, 3, 4, 7, 8. Okay, so all we're doing is taking a log function and we're moving it left or right, up or down, reflecting it or stretching it. Okay, so if we had our log equation, these all still work the same way. Okay, so if A is positive, or sorry, I should just say if A is negative, then we're going to have a reflection on the x-axis. X-axis, so that means all your y's change to opposite signs. Nope. But the values change, they're still x and y. Yes. Be your y's, and your y's would now be your x's. Yep. Okay, so C is still just the base of the function. B is, oh, we have to talk about A as being a stretch too, right? A vertical stretch. Because if A is 2, then our y values are now 2 times as big. If A is a half, then our y values are now half as big. Okay, same goes with B, except it's a horizontal stretch. And the opposite happens. Horizontal, did I spell that right? It looks horrible. Horizontal stretch. So if B is a quarter, then our x's are 4 times as big. And if B is 3, then our x's are a third the size, right? So it's the opposite thing happening there for the horizontal stretch. What else can we say? H is a horizontal translation. So that just means if it's positive, you're going left. And if it's negative, you're moving right. And K is a vertical translation. Up or down. It's exactly the same thing. It's just a log equation. Okay. So we're going to do the exact same thing. We're going to get our basic log table, and then we're just going to change it depending on what's happening with our equation. Okay, so for example 1, I will change the slide. Are we all good? Okay, so example 1 says, use transformations to sketch the graph of the function y equals log 3 x plus 9 plus 2. Okay, so if we want to think of our simple basic log equation and then we're going to transform it, it would look like this. Okay, just 3x. And then what's happening is we have a 9 and then the 2 is affecting it also. Okay, so but our basic just generic log equation would be log whatever our base is with x. Okay, so if we were going to make a table from that, you just need to think of it as exponential, right? So this was our base, this is our answer, and then we just have to figure out what our exponent is. So, hold on. Okay, so I'll put y there for my exponent. Okay, so if I was making a table, if x was 1, what would my y have to be? 3 to the power of what gives you 1? Yeah, 0. Okay, so this is where my original table comes from. Because if I put, how do I get rid of that? If I put 1 here, 3 to the power of what gives you 1? Well, 3 to the power of 0 does. Okay, so say I had a 3 for my x value. I'm just picking random x's, by the way. If I had 3 for my x value, 3 to the power of what gives me an answer of 3? Yeah, 1. Okay, so there we go. And then I'm just picking things that are like multiples of 3, by the way, just because that's what my base is. If I had a base 2, I'd probably go 2, 4, 6, something like that. Okay, so say I went with 9 here. 3 to the power of what gives me 9? 2. Okay, so this is my table that I'm going to start with. Okay, this is just my generic table. And then I'm going to do the transformations to it. Okay, so this, what's happening there? What does that mean? Yeah, a horizontal translation, so we're going to move which way how much? Yeah, we're going to go 9 left. So we're subtracting 9 off of all of our x's, right? So we're going to minus 9 off of all of these. We don't have any reflections or stretches or anything. Otherwise, we'd have to do that first. And then what's that plus 2 here? So we said this was a horizontal translation. Vertical translation to up. So that means we're going to add 2 to all of our y's. If I can write it. Okay, so my new table is going to be minus 9 plus 1 is minus 8, minus 6, and 0. And then I have 2, 3, and 4. Okay, so now it's just as easy as graphing that last table. Okay, so all we have to do is graph those points. So we are at minus 8 and 2 and minus 6 and 3, and then we're at 0 and 4. So this is what it looks like, kind of. And remember, our asymptote used to be on the x-axis, but now we moved it back 9, so now it's at negative 9. Okay? So the next part of this question says, oh, I just answered that one. I says, what's the equation of the asymptote? It would be at x equals minus 9, because we went backwards minus 9. Okay? The second part says, what's the domain and range? So the domain, if we're looking at it, we're only from minus 9 and greater. So we'd say x has to be greater than minus 9. And our range looks like it goes up, and it shouldn't really taper off. It should still be going kind of up, 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 right? So it's at XER. The y-intercept, we drew it on here, was at 4. So y equals 4. And then the only thing that we actually have to do a little bit work for is it says the x-intercept, if it exists. So we're crossing somewhere here right before we hit that minus 9 because we can't hit that line, right? So our x-intercept's going to be like 8 point something. Okay, so in order to solve for that, we have to remember our log equation, how we solve for logs. So here's our equation. And we're going to let 0 equal y, right? Because if we want an x-intercept, you put 0 for y. So our equation was this, right? Okay, and usually we'd have something and then equals something. So let's minus this 2 over, so that we actually have minus 2 log base 3 x plus 9. Okay, and now we remember from yesterday in 8.1 we said this was the base, the answer, and the exponent, right? So base 3, our answer is x plus 9, and our exponent is minus 2. Okay, so now all we have to do is solve for x. So 3 to the minus 9, or 3 to the minus 2 is 1 over 9. because you make it 1 over 3 squared. Okay, and that equals x plus 9. So we want x by itself, we minus 9 and minus 9. Okay, I'll just go over here. So minus 9 plus 1/9, you have to make those the same denominator. So I'm just making my minus 9 minus 81 over 9. I just times them both by 9. And then it's plus our 1/9 is equal to x. So we end up with minus 80 over 9 for x. Okay, and if you actually divided that, I think it is negative 8.9. So that's what we were saying. It has to be somewhere really close to negative 9 because that's the line we're not crossing. So our x-intercept is minus 8.9. So example 2 says we have y equals negative log 2x plus 6. Okay, as soon as we see something right with that x, we have to divide out by it because we can't have him right with our x. So we'll divide by 2 and divide by 2 here. So we actually have y equals minus log base 2, and now we have 2 and x plus 3. Okay, so when you write it like that, now it's easier to see that that's a horizontal stretch. Okay, so in this question we have this, which is a reflection on the x, so that's going to change your y values. So reflection on x-axis, that's going to change your y values. This guy is a horizontal stretch of a half, right? Because he's always the opposite. And then this guy here is a horizontal translation of negative 3. Okay, so everything, the reflection is going to change our y values to the opposite sign, and then the other two things are going to change our x values. Okay, so if we go with a basic table again. Okay, so I'm going to start with just a generic table. So remember, that would be like if, whoops, not like that. Like if we had an equation like that, y is equal to log 2x. Meaning this is our base, our answer is x, and our exponent is y. Okay? So if x was 1, remember, if x was 1, our y would have to be 0, because anything to the power of 0 is 1. Okay, and then if x was 2, our y would be 1, because 2 to the power of 1 gives you 2. And then if x was 4, this would be to the power of 2. And if we want to go farther, I don't know if I can fit it on here, but 8 and 3, right? Because 2 to the power of 3 is 8. Okay, so now we just have to change all of our tables according to what's happening. Okay, so our next table, we always are supposed to do reflections and stretches first. So we're going to change all our y values. What happened to my 0? Did I not draw it ever? Oh, it just didn't show up. Okay, so all our y values are going to change to the opposite sign. So 0 is still 0. And then we have negative 1, negative 2, and negative 3. Okay, and then we might as well do our stretch, meaning all of our x values are going to be half as big. So 1 divided by 2 is 0.5, or a half. 2 divided by 2 is 1. 4 divided by 2 is 2, and 8 divided by 2 is 4. Okay, so all I did was divide by 2 for each of my x values. Okay, and then we're almost done. All we have to do is subtract 3 right, to move for our horizontal translation. So we'd minus 3, minus 3, minus 3, and minus 3. So our last and final table is going to be minus 2.5, minus 2, minus 1, and 1. And then our y's are still 0, minus 1, minus 2, and minus 3. And then all we would do is take those points and then graph it and then answer the questions just like we did in example 1. Okay, the last example, I don't have the graph on here, but you can see it in your notes. It's saying determine the equation of the log function. So the original one is y is equal to log for x. So that's the lower one. And then the one above it is the new equation. So we want to know what happened to it. So if you look, that one point is at 4 and the other one is at 1. Do you see those points that are marked on there? The one is at 4 and 1 and the other one's at 1 and 1. Okay, so what happened to that? It was 4 times the size and now it's not. Right? So it would actually be this way. Yeah. Because our x value was 4 and now it's 1, right? Because I can't really show the picture here, but okay, so this, say this point was 4 and 1, and then on this new graph it's 1 and 1. Okay, so the x value shrunk by 4, right? So how you would write it, yeah, well, it shrunk by 4, so you have to write it as 4x, because you always do the opposite, right? So that looks like your x's are being times by 4, but they're actually divided by 4. Okay, so this would be the equation of the transformation.